Did you know that you may feel completely relaxed and at peace right now, but the Earth is still silently carrying you across the universe in a gentle and unceasing motion? The Earth is far from motionless at this very moment. You are rotating at more than 1,670 kilometers per hour, while hurtling around the sun at nearly 108,000 kilometers per hour. Every sunrise you have ever watched was never the sun drifting across the sky. It was you and the world beneath you slowly turning into the glow of daylight. Part 1. The sun remains still, the Earth rotates. With every moment directly below your feet, the surface is spinning, sweeping you eastward at a speed greater than that of sound. You cannot sense it yet, it is ceaseless. Every building, every coastline, every stretch of desert, all of it whirls through space at 1,670 kilometers per hour around the planet's axis, and simultaneously the entire globe races around the sun at almost 108,000 kilometers per hour. This means that even when you appear completely motionless, you are traveling tens of thousands of kilometers each hour, and yet the experience is one of perfect stillness. That illusion, the sensation of calm in the midst of motion, stands among the most remarkable ideas in physics. It explains why the sun seems to rise and fall, though in reality it never shifts at all. Each morning is not the sun returning to us, but our turning world presenting its face to the light once again. Earth completes one rotation every 23 hours, 56 minutes and 4 seconds, a cycle just shy of 24 hours. Astronomers describe this as a sidereal day, defined by the time required for the planet to spin once relative to the distant stars. The 24-hour day we follow is slightly longer because as Earth rotates, it also advances through its orbit, and it must rotate a bit further each day for the same region to face the sun once more. That small discrepancy, a mere 4 minutes, shifts the sky night after night. In the span of 1 month, those minutes amount to 2 hours, and over a year they accumulate into an entire day. So the stars shining overhead this evening do not occupy the same positions they held last season. Their drift is not the universe itself moving, but the result of our own journey through space. Long before satellites or the precision of atomic timekeeping, ancient observers recognized this pattern. They traced the changing lengths of shadows and charted the slow migration of constellations. The Egyptians constructed their monumental temples so that sunlight would illuminate a single point only once each year, a celestial rhythm carved into stone. Today, the same patterns are verified by the National Aeronautics and Space Administration through very long baseline interferometry, comparing radio waves from remote quasars to measure Earth's rotation with astonishing accuracy, down to a fraction of a millisecond. Yet the rotation is not perfectly uniform. Winds rearrange, oceans shift, glaciers melt. Each movement redistributes mass across the globe and subtly alters the planetary spin, much like a figure skater adjusting their speed by drawing in their arms. After major earthquakes, the Jet Propulsion Laboratory has detected tiny changes in the length of a day, sometimes measured in only a few microseconds. And it is precisely this consistency, this delicate steadiness, that allows life to flourish. Rotation moderates temperature, powers the great atmospheric streams, and shapes the alternating pattern of light and darkness that governs every living system. Without it, the Earth would be utterly transformed. A thinker once remarked that the Earth is a small stage set within a vast cosmic theatre. That sentiment captures something profound. The Earth is indeed a stage, but a stage in constant motion, turning endlessly under the unseen laws of angular momentum that bind us to every spinning structure in the universe. From the tiniest electrons to immense galaxies, rotation is one of the universe's most enduring signatures. Consider this. Right now, your body, the air you breathe, and even the atoms woven into your bones all share the same sweeping velocity. That is why the motion is imperceptible. Everything familiar to you moves together as a single synchronized whole. It is the purest demonstration of inertia we ever encounter. And if the Earth were to halt its rotation in an instant, even for a single second, every object not firmly anchored to the crust, would continue its eastward path at more than 1,670 kilometers per hour. Oceans would sweep across entire continents, winds would tear at the very skin of the world, and the planet's delicate balance would unravel. It is a hypothetical vision explored by geophysicists as they investigate how the energy of rotation governs the stability of planets. Using data from the Gaia, mission researchers have also detected a slow and graceful wobble in Earth's axis, a motion called axial precession, which completes a full cycle roughly every 26,000 years. That gentle drift gradually shifts the direction of Earth's poles and even determines which star we recognize as the North Star. Thousands of years in the past, it was not Polaris, but Thuban in the constellation Draco. So even our sense of what north means is temporary. Everything we assume to be a fixed reference point, including daylight and the very notion of a day, arises from layers upon layers of motion. And yet within that intricate dance there is a kind of calm, because despite the constant shifting, Earth remains steady enough for us to live, breathe and rest. The same physical laws that drive us through the cosmos also cradle us in a remarkable equilibrium. So when morning arrives, remember that the sun did not rise at all. You did. The ground beneath you has never ceased to turn, and it never turns at exactly the same speed. As Earth travels through space, it accelerates and decelerates following an invisible path that changes from day to day. And as we continue along this quiet celestial voyage, a question lingers. Part 2. Why does the sun seem to quicken and slow throughout the year? Perhaps you have noticed that the sun is an unreliable timekeeper. Some mornings it climbs above the horizon, a few minutes early. On other days it hesitates, dipping below the horizon later than expected. Even the most precise clock cannot perfectly follow the sun because the sun's apparent pace across the sky subtly shifts. But the truth is that the sun's speed does not change. It is Earth that varies. Our planet does not travel around the sun along a perfect circle. Instead, it moves in an ellipse, a slightly elongated orbit, first described by Johannes Kepler in the year 6009. Kepler's second law, or the law of equal areas, tells us that a planet moves more quickly when it is closer to the sun and more slowly when it is farther away. In January, Earth reaches perihelion, its nearest point to the sun, at roughly 147 million kilometers. By July, it arrives at aphelion, about 152 million kilometers distant. That modest difference of around 5 million kilometers shapes the entire rhythm of our sky. Near perihelion, Earth's orbital speed rises to about 30.3 kilometers per second. 6 months later, at aphelion, it slows to roughly 29.3 kilometers per second. This variation of 1 kilometer per second may seem insignificant, but over millions of kilometers it alters the sun's apparent motion as seen from Earth, stretching and compressing our days in subtle but measurable ways. Astronomers refer to this phenomenon as the equation of time. It is one of the most quietly captivating adjustments in celestial mechanics, a mathematical explanation for why solar time and clock time never align perfectly. If you were to measure time by watching the sun cross the meridian above you and compare that moment with the reading on your watch, you would discover a small but persistent mismatch. At times the sun appears ahead, at other times it lags behind. Across a year, that difference can reach about 16 minutes. This fluctuation arises from two primary causes: the elliptical nature of Earth's orbit and the tilt of its axis. The tilt alters the sun's apparent motion across the sky as the seasons change, while the elliptical path alters Earth's orbital speed. Together they make the solar day the interval between two noons, slightly longer or shorter than 24 hours. In early January, when Earth moves most rapidly around the sun, each solar day becomes a little longer than average. Around early July, when our planet travels more slowly, the solar day becomes slightly shorter. The difference can be around 30 seconds per day, accumulating into shifts that become noticeable over the months. This is why sundials, ancient yet elegant instruments, do not always agree with the clock on your phone. The sun is indifferent to human schedules. It is governed purely by physics, not by calendars. Observations from the Solar Dynamics Observatory monitor these changes by recording the sun's apparent motion against the background of the sky. When scientists chart the sun's daily motion across an entire year, its path sketches a delicate figure 8 in the sky, a pattern known as the analemma. It appears on certain globes as a slender looping form near the Pacific Ocean, shaped by the tilt of our world and by the subtle changes in its orbital speed. That graceful curve is a portrait of imperfection, a reminder that the journey of our planet is slightly asymmetric, slightly offset, and yet profoundly predictable. It reveals that what we call time is not a uniform beat, but a consequence of motion. During December and January, as Earth moves fastest along its orbit, the Sun seems to drift behind schedule, reaching the meridian a little later each day. By March and September, it catches up again. These variations are the reason the earliest sunset and the latest sunrise do not occur on the solstice, but instead arrive weeks on either side. The equation of time quietly explains why the longest day of the year, the summer solstice, is not matched by the earliest sunrise. Modern calculations from the Gaia mission and the Horizon system at the Jet Propulsion Laboratory now capture these orbital changes with extraordinary accuracy. The data shows that Earth's velocity and distance shift in a reliable yearly pattern, and even the faint gravitational pulls from the Moon and the other planets introduce minuscule but measurable deviations. When those influences align with subtle precision, the orbit of our world breathes gently, a cosmic inhalation and exhalation repeated every year for billions of years. And despite all this complexity, the daily consequence is something you can notice without any instruments at all. If you have ever looked up on a winter morning and felt the sunlight arriving later than expected, you have already perceived the equation of time. It is the silent clockwork of the cosmos, a clock that never deceives us, but never repeats exactly. As one physicist once remarked, the universe is under no obligation to make sense to us. The sun's uneven motion is a quiet testament to that idea. What appears irregular from our perspective is in truth governed by laws, shaped by geometry, by gravity, and by angular momentum. Why does this matter? Because it reveals that time, even the kind ticking gently on your wrist, is not absolute. It is constructed from motion, and motion shifts with distance and with speed. The equation of time forms the link between the time kept by humanity and the time kept by the sun, between our desire for order and the restless intricacies of celestial mechanics. It also demonstrates how far precision in astronomy has advanced. In the 18th century, sailors navigating across the oceans relied on this understanding to determine longitude. They compared the observed position of the sun with the expected mean solar time. A single minute of error could translate into a position offset of roughly 28 kilometers. That is why the creation of the marine chronometer in the year 1761 transformed navigation. It enabled humans to measure time with the reliability required to cross vast oceans safely. Today, atomic clocks aboard the satellites of the Global Positioning System depend on even more refined corrections. They account not only for the equation of time, but also for the effects of general relativity, because the flow of time itself changes with altitude and with velocity. Without these corrections, errors in the system would accumulate at a rate of about 10 kilometers with each passing day. So when your phone displays the precise time, it is actually drawing upon the work of generations of scientists from Einstein to Kepler, and upon centuries of watching the heavens, all to synchronize your heartbeat with the turning of a rotating, orbiting world. The next time you glance at a clock and notice the sunset arriving slightly earlier or later than expected, remember that the fault is not with your clock. It is simply Earth following its ancient elliptical rhythm. The equation of time is more than a mathematical curiosity. It is a reflection of our planet's exquisitely imperfect perfection, evidence that nature never repeats itself exactly, and that even the most familiar cycles hide subtle variations. So tomorrow, when the sun rises, not quite the moment you expect, pause for a quiet instant. You are seeing one of the most delicate harmonies in celestial motion, a balance shaped by gravity, by geometry, and by time itself. As we continue to trace this symmetry through the turning of the seasons, one question naturally emerges. If time bends with motion, then what are we truly measuring when we measure a day, because if our clocks depend on Earth's imperfect rotation, then perhaps what we call time is only a shadow, not the underlying reality. Part 3. Does true time genuinely exist? Consider a curious fact. There is no single moment shared by everyone across the universe. Even this instant, as you listen, does not occur simultaneously everywhere. The faster you move, or the stronger the gravitational field you inhabit, the more slowly your clock runs relative to mine. This is not philosophy, it is physics. The moment humanity chose to measure time with clocks instead of the sun, we quietly stepped away from Earth's natural rhythm. For thousands of years, a day meant one full rotation of the planet, one sunrise, one sunset. But as our instruments improved, we uncovered something deeply surprising. Nature's time and human time rarely walk in step. In the early view of classical mechanics, time was treated as something absolute, flowing steadily and uniformly through the entire cosmos, untouched by circumstance. It was an idea that suited the world of Isaac Newton, who wrote that absolute, true and mathematical time flowed impartially from its own nature, uninfluenced by anything beyond itself. Yet in the year 1905, Albert Einstein overturned that comfortable certainty. His special theory of relativity revealed that time is not a detached stage on which events unfold. Instead, it is interwoven with space into a single fabric known as space-time. Within this framework, time gains meaning only when compared to motion. As an object increases its speed, the passage of time for that object slows when observed from a stationary frame. This phenomenon, called time dilation, has been confirmed repeatedly in experiment. In 1971, scientists Halley and Keating flew atomic clocks aboard commercial aircraft, circling the planet in opposite directions. When the airborne clocks were compared to identical ones left on Earth, the differences amounted to mere billionths of a second, precisely matching Einstein's predictions. Today, the same correction is essential for the global positioning system satellites that orbit Earth. Each satellite travels at roughly 14,000 kilometers per hour, and because they orbit farther from Earth's gravitational pull, their clocks run slightly faster than clocks on the ground. Without the continual application of Einstein's relativity equations, the global positioning system would drift by 10 kilometers every day. So when your phone pinpoints your location, it quietly relies on general relativity to reconcile motion and time. Modern physics extends this understanding even further. In general relativity, time itself bends in the presence of mass. Where gravity is stronger, time slows. Near a black hole, a handful of seconds can stretch into hours. In 2019, NASA's Event Horizon Telescope produced the first image of the shadow of the black hole in the galaxy M87, a region where gravity bends not only light but the flow of time itself. Einstein expressed this elegant relationship simply: mass tells space how to curve, and space tells matter how to move. The result is a universe in which time flows differently from place to place. As NASA describes, clocks slow down near massive objects and speed up as you move away from them. What we call a second is a local measure, valid only within Earth's particular gravitational field and rotation. Elsewhere, that same second stretches or shrinks. There is no universal metronome marking time for the entire cosmos. When we descend to the realm of quantum mechanics, the picture becomes even more peculiar. On subatomic scales, time ceases to behave as a smooth continuum. Particles do not follow graceful, continuous paths. Instead, they inhabit clouds of probability in which time seems to pause between interactions. Experiments at CERN and other laboratories hint that time, like matter itself, could emerge from deeper laws of physics. It may not be a fundamental ingredient of reality, but a statistical consequence of countless microscopic events. If all motion were halted, if every atom, photon and planet came to rest, the equations suggest that time would simply disappear. Time, in its most elementary sense, is the measure of change. Without change, it has no meaning. ESA's Gaia mission has created one of the most precise temporal frameworks ever constructed, a kind of cosmic chronometer built from the motions of more than 1.5 billion stars. Yet, even with such exquisite data, the universe reveals itself as perpetually in motion, from the largest galaxies to the smallest particles. Absolute stillness is nowhere to be found. This leads to a profound conclusion. A single universal moment, a true cosmic now, does not exist. Every location in space experiences its own flow of time, determined by its velocity and gravitational environment. Astronomers refer to this as proper time, the time measured within an object's own frame of reference. On the International Space Station, astronauts circle Earth every 90 minutes at 7.6666 kilometers per second. Over a period of 6 months, their clocks fall behind Earthbound clocks by about 0.01 seconds. The difference is tiny yet real, and when they return home, Mission Control must adjust their recorded time to align with Earth's. The most precise timekeeping devices ever built, the optical lattice clocks can detect a difference in time between 2 points separated by just 1 centimeter in height. At such precision, simply standing upright means that your head ages infinitesimally faster than your feet. As NASA physicist Don Lind once remarked, "Everywhere is local time." This is not a mere scientific curiosity. It represents a profound revision of our understanding of existence. Time is not an external river flowing past us. It is a dimension shaped by motion and mass. It stretches, compresses, and responds to energy itself. If every oscillation, every wave, every particle in the universe were frozen, time would halt. There would be no before or after, no aging, no sequence of events. The cosmos would become a single, unmoving tableau. But such stillness is impossible for our universe. Motion forms the very weave of reality. Time arises only because everything in the universe is in motion. That is why, in the language of physics, time cannot be separated from space and energy. In the field equations of Einstein, it is not treated as a passive backdrop. It is an active element of the curvature of space and time. When scientists at agencies like the National Aeronautics and Space Administration simulate the unfolding of the cosmos, they do not push time forward step by step. They calculate how the density of energy reshapes itself. And what we call time is simply how that transformation appears to an observer living within the system. Even the James Webb Space Telescope acts as a kind of vessel for travelling into the past, not because it alters time, but because light itself carries the imprint of time along its journey. When the telescope captures the glow of a galaxy 13 billion light years away, it is witnessing light that began its voyage 13 billion years ago. In that sense, telescopes do not merely peer across space, they peer through deep layers of time. Every photon is a marker of a moment. Every wavelength holds the story of motion, energy, and decay. When we study the universe, we are not observing an object distant from us. We are interpreting the written record of time itself. So does time truly exist on its own? According to every modern measurement, the answer is no, not as a standalone substance. Time is not a universal backdrop. It is relative, local, and shaped by motion. That understanding transforms the way scientists construct models of the universe. Cosmological equations are built from intervals in space and time, not isolated instants. Even the age of the universe, 13.8 billion years, is defined within the reference frame of the cosmic microwave background, rather than as an absolute value valid everywhere. For most of human existence, we assumed time was something waiting to be measured. Now we understand it as something generated by motion, gravity, and the act of observing. And that may be among the most humbling insights of all. The flow of time is not a cosmic directive imposed from the outside. It is the dynamic outcome of everything that moves within the universe. Tomorrow, when you glance at your clock, consider this. Those passing seconds are not fixed. They are linked to the rotation of the planet, to your height above sea level, and to your motion through space. Each tick is a subtle reflection of your position in the cosmos. And as we go further, we will trace that ticking more deeply to uncover how the very idea of noon shifts from one location to another, and why even the notion of midday varies among people standing beneath the same sun. Part 4. Noon is not identical everywhere on Earth. Right now, at some point across the globe, it is 12 noon according to the clock, yet the sun is not directly overhead. In truth, for most places on Earth, it almost never is. The clock may declare midday, but the sky often tells another story. This small discrepancy between the time displayed on a watch and the behavior of the sun is one of the quiet consequences of the way our planet spins and leans through space. It also reveals how humanity slowly replaced natural time with an artificial construct. The true physical definition of noon, known in astronomy as local apparent solar noon, is straightforward. It is the instant when the sun crosses your meridian, the unseen line running from north to south through your position. At that moment, the sun reaches its highest point in your sky. Shadows shorten to their minimum length. But because the Earth rotates unevenly and its axis is tilted by 23.4 degrees, this moment of genuine noon rarely aligns with 12 according to the clock. Move east or west by a single degree of longitude, roughly 111 kilometers, and true noon shifts by about 4 minutes. Even two nearby towns can experience the sun's peak at slightly different times. Before mechanical clocks arrived, people lived by this solar cadence. Each settlement kept its own local time, based on the sun's path. Noon was simply when the sun reached its highest point, and that sufficed. But in the 19th century, railways and telegraph lines bound cities together. Local time no longer worked. A train could not operate safely if noon changed every few kilometers. So in the year 1884, at the International Meridian Conference in Washington, District of Columbia, scientists and diplomats agreed to divide the Earth into 24 time zones, each spanning 15 degrees of longitude. They established the prime meridian through Greenwich in England, and from that line the system of standard time emerged. Time zones resolved the confusion, but they also quietly concealed the natural irregularities of the planet. When your phone jumps to a new time as you cross a border, it is following a human design, not the reasoning of the sun. For example, even when the clock in Paris strikes noon, the sun has already passed its highest point in the sky. In Beijing, a city that spans 5 theoretical time zones yet lives by only one, noon can arrive while the sun is still climbing toward its peak. This disconnect can stretch to nearly 2 hours between the moment the sun stands highest in the sky and the moment our clocks declare midday, all depending on your position within a time zone. In Spain, for example, the true solar peak often occurs around 2 o'clock in the afternoon. Standard time, shaped by political choices made during the year 1940 seconds, reflects a simple truth described by researchers at the National Aeronautics and Space Administration's Goddard Space Flight Center. The sun does not obey our clocks. Our clocks obey practicality. What began as a sensible adjustment became a quiet divergence between the rhythms of human society and the natural rotation of the Earth. Yet even solar noon itself refuses to be fixed. The Earth travels along an elliptical orbit, and its rotation subtly quickens and slows throughout the year, as outlined by Kepler's laws. This causes the sun's apparent position to wander by as much as 7.5 degrees north or south of its average path. The result is what we call the equation of time, the difference between true solar time and the average time we rely on. Because of this, the moment of true noon can drift by as much as 16 minutes over a single year. If you photograph the sun from the same location at the same clock time every day, the traced path is not a straight line, but a looping figure eight. This is the analemma, once commonly printed on old globes, a graceful signature created by the tilt of the Earth, combined with its imperfect orbit. With data from the Gaia mission and the Jet Propulsion Laboratory's Horizon system, scientists can now model these variations down to fractions of a second. The precise instant of solar noon at any position on Earth can be forecast centuries ahead, a testament to the unwavering reliability of orbital mechanics. And still, despite such precision, our lives unfold according to averages, according to mean time, rather than the shifting reality overhead. All of your clocks are synchronized to coordinated universal time, maintained through atomic clocks that track the oscillations of cesium atoms at a rate of 9,192,000,000 631,700 cycles per second. But the Earth does not rotate in perfect harmony with this standard. Its spin gradually slows as tidal forces from the Moon siphon away angular momentum. To keep coordinated universal time aligned with the Sun's rhythm, international timekeepers occasionally add a leap second, a single extra heartbeat of time, to prevent our systems from drifting away from the planet's true rotation. The most recent leap second was introduced in 2016. Physicists at the National Aeronautics and Space Administration describe this delicate balance as a kind of temporal maintenance. It is our way of keeping human time from slipping too far from cosmic time. But as atomic clocks grow ever more stable and the Earth's rotation continues to slow in unpredictable ways, scientists are now debating whether to abandon leap seconds altogether. Should that happen, our civil timekeeping will gradually separate from the solar cycle by about 1 minute every 50 to 100 years. At first, the drift would be almost imperceptible, but eventually noticeable. One day, noon on the clock could arrive while the sun is still rising. In many respects, this drift has already begun. Artificial light frees us from solar schedules. Global positioning satellites and atomic clocks define time far beyond human intuition. Time zones rooted in political decisions rather than physical reality, to organize how we sleep, work, and live. And yet beneath this framework, the natural world continues its precise and indifferent rhythm. The real sun still crosses each meridian once every day, whether or not we turn our eyes upward. It has been said that we belong to the universe and exist within it, but perhaps just as profound is the idea that the universe exists within us. The same is true of time. Every second we count is borrowed from the celestial choreography that carries our planet forward. When the sun climbs to its highest point tomorrow, it may not be exactly 12. It might be a few minutes earlier or later, depending on your longitude, the date, and the geometry of the Earth's orbit. That quiet discrepancy, that gentle imperfection, is one of astronomy's most beautiful truths. No 2 points on Earth ever share the same noon. So when your clock strikes 12, remember that the universe has not shifted to suit your expectations. Instead, humanity has adjusted the cosmos into its timetable. And if we follow this adjustment deeper, something subtle emerges. The more precisely we measure time, the clearer it becomes that the Earth is not simply spinning, it is drifting through an immense invisible river of motion. Which brings us to a greater question, part 5. Where is the Earth truly travelling at this very moment? Even as you sit or lie still, you are sweeping through the galaxy at nearly 792,000 kilometers per hour. You do not feel it, because everything around you shares the same vast journey. But be certain the ground below, the air above, even the sun itself, all of it hurtles through space. The question is, where is this collective voyage taking us? Most people know that the Earth spins once every 23 hours and 56 minutes. It also completes an orbit around the sun every 365.25 days at roughly 108,000 kilometers per hour. But these are merely the first layers of motion. Beyond that, there is an even deeper and swifter drift, a motion that carries not only Earth, but the entire solar system through the Milky Way galaxy. Our sun, together with its family of planets, moons, and asteroids, follows an orbit around the center of the galaxy, a location approximately 26,000 light years away, in the direction of the constellation Sagittarius. Astronomers have determined that this central region conceals a supermassive black hole called Sagittarius A*, with a mass about 4 million times greater than that of the Sun. Even across this vast distance, gravity governs everything. The Sun traces an orbit that is roughly circular, completing a single revolution around the Milky Way every 230 million years, a span often described as a galactic year. During this immense journey, Earth and all life upon it travel about 9 trillion kilometers. According to the Goddard Space Flight Center of the National Aeronautics and Space Administration, our entire solar system orbits the Milky Way's center at a speed of roughly 220 kilometers per second, which is more than 792,000 kilometers per hour. And yet the stars around us appear almost motionless because they too participate in this grand motion. But the Milky Way itself is far from still. The European Space Agency's Gaia mission, which measures the positions and motions of more than 1.5 billion stars, has revealed that our galaxy is moving toward a mysterious region of the cosmos known as the Great Attractor, situated between the constellations Leo and Virgo. The Milky Way and nearby galaxies, including Andromeda, Triangulum, and thousands of others, are being drawn toward this gravitational anomaly at a speed of about 2.1 million kilometers per hour. The Great Attractor is not a single object, such as a black hole or a star cluster. Instead, it is a gravitational focal point within a vast region of space called the Laniakea supercluster, which contains more than 100,000 galaxies stretching across 520 million light-years. Data from the Center for Astrophysics at Harvard and the Smithsonian show that the Great Attractor marks the direction in which our entire cosmic region is flowing, a vast gravitational valley guiding the paths of galaxies, much like rivers, following the contours of a landscape. And even this colossal structure is not stationary. Beyond it lies yet another gravitational flow toward the Shapley supercluster, even more distant, indicating that the large-scale structure of the universe is in continuous motion. This means that every location in the cosmos, from the tiniest particle of dust to the largest assembly of galaxies, is always moving relative to something else. There is no fixed center, no absolute up or down. As astrophysicist Michelle Thaler of the National Aeronautics and Space Administration has noted, there is no place of rest in the universe. Everything orbits something else. To put this in perspective, while you sleep for 8 hours, Earth rotates about 120 degrees relative to the stars, travels 864,000 kilometers along its orbit around the Sun, and is carried 6.3 million kilometers through the Milky Way. Yet none of this is sensed. Why? Because all of these motions are shared. The air, the oceans, and your own body all move together as part of a single inertial system. Within that frame, you feel motionless, even as the entire planet sweeps through the darkness at extraordinary speed. This is one of the most profound truths of physics. Motion is relative. Without an external point of reference, constant velocity cannot be detected. Only acceleration, a change in speed or direction, can be measured. Since Earth's orbital and galactic motions are nearly uniform, they remain quiet, steady, and imperceptible. Gaia data have also shown that the Sun's path through the Milky Way is not flat. It rises and falls through the galactic plane in a gentle wave, reaching about 70 light-years above and below the disk, completing a full vertical cycle every 64 million years. Some researchers have even proposed that these oscillations might influence the frequency of comet impacts on Earth as the solar system periodically moves through denser regions of interstellar material. And this layered pattern of motion extends even farther. The Milky Way belongs to what astronomers call the local group, a modest gathering of galaxies that includes Andromeda, also known as M31, and Triangulum, known as M33. All of them are held together by the gentle yet insistent pull of gravity, gradually drawing closer over immense stretches of time. In roughly 4 billion years, the Milky Way and Andromeda will collide and combine into a single vast elliptical system, a future written clearly in the data from the Gaia spacecraft, which measures Andromeda's approach at around 110 kilometers per second. Far beyond that, the local group resides within the Laniakea supercluster, and this entire region is gliding through space relative to the cosmic microwave background, the faint afterglow of the Big Bang, at a speed of about 630 kilometers per second. Scientists determine this drift by observing the cosmic microwave background dipole, a tiny temperature variation across the sky produced by our motion through this primordial light. It means that even the fading echo of creation reminds us that we are never motionless. Every moment carries us into new realms of space-time coordinates we will never occupy again. When you lift your eyes to the night sky, you see ancient light, but you yourself are moving through the scene. The stars you gaze at tonight no longer sit where they once did thousands of years ago. Some have already ended their lives, their final photons still crossing the dark to reach us. There is a line that speaks to the brevity of our experience. We flutter for a moment and imagine it to be forever. In the context of cosmic motion, this captures our condition perfectly. We are temporary travelers on a world in motion, orbiting within a system in motion, inside a galaxy, adrift in an expanding universe. This picture arises not from poetic speculation, but from measurements. Radio telescopes track Doppler shifts. Gaia charts the proper motions of stars. Observatories studying the microwave sky, such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite, reveal the subtleties of our velocity with remarkable clarity. Planck confirmed that our galaxy itself speeds through space at about 370 kilometers per second relative to the cosmic microwave background, showing that the Milky Way takes part in a grand cosmic flow. So if we ask where Earth is headed, the scientific reply is that we are moving everywhere and nowhere fixed. We inhabit nested cycles of motion, each governed by gravity, each part of a greater whole. From the spin of electrons to the rotation of stars, movement is the defining characteristic of existence. It is not unusual, it is universal. And although we have charted much of this motion, the ultimate destination remains uncertain. The great attractor of vast gravitational anomaly shaping our region of the cosmos remains partly concealed behind the zone of avoidance, a band of sky hidden by the Milky Way's dust and gas. The James Webb Space Telescope is now examining this region in deep infrared wavelengths, capable of piercing that obscuring material, offering views into what shapes this immense gravitational pull. Early findings point toward colossal galaxy clusters and concentrations of dark matter sculpting the gravitational landscape, perhaps among the largest known structures near our cosmic neighborhood. Each new observation reinforces a single idea. Space itself is dynamic. The cosmic web, a tapestry of galaxies stretching across billions of light years, bends, collapses, and stretches, carrying us along. From the space around you to the most distant quasars, no position is permanent. Every location participates in a wider motion. If time could be frozen and your coordinates marked a single second later, you would find yourself billions of meters away in the Milky Way's frame of reference. The ground feels unmoving only because we all journey together. This is one of the quiet revelations of astronomy. Motion is not something happening to us. It is something we are embedded within. Tomorrow, as you stand beneath the sun, imagine the invisible arcs you trace. Earth rotating, orbiting, and spiraling through the Milky Way, all of it drawn toward a distant region no one has yet seen. And if everything moves, then the notion of a day becomes far more subtle than it seems. A day is not truly 24 hours. Every clock on Earth is slightly misleading. We are taught that a day lasts exactly 24 hours, yet in astronomical terms this is not entirely accurate. Earth does not require 24 hours to complete a single spin. It takes 23 hours, 56 minutes and 4 seconds, a span known as the sidereal day. The missing 4 minutes reveal a delicate truth about how our planet travels through the cosmos. A sidereal day measures one full rotation of Earth relative to the distant stars, the fixed backdrop of the universe. It is the most precise measure of planetary rotation. But as Earth spins, it also advances along its orbit around the Sun. During one rotation, it travels roughly 2.5 million kilometers along its orbital path. So after completing a full 360-degree turn, relative to the stars, the Sun is no longer in the same position in the sky. To bring the same longitude back into alignment with the Sun, Earth must rotate a little more, about 1 additional degree, which takes roughly 4 minutes. That is why the solar day, the interval between successive noons, lasts 24 hours. The sidereal day is shorter because the stars provide a fixed reference while the Sun appears to shift as Earth makes its yearly journey around it. This small mismatch may appear insignificant, yet it reveals a profound distinction between the way humans sense the passage of time and the way astronomers chart the dance of worlds. A sidereal day marks Earth's rotation in relation to the distant stars, while a solar day measures that rotation in relation to the sun day. The difference is roughly 4 minutes. And that quiet 4-minute drift accumulates quickly. After 1 month, the stars seem to rise about 2 hours earlier than they did at the start. After 1 year, the shift completes a full 24-hour loop, which is why the constellations that fill the night sky transform with the turning of the seasons. In July, the constellation Scorpius stretches across the southern horizon. 6 months later, in January, Orion takes its place. This cycle forms one of the most fundamental rhythms in all of observational astronomy. Telescopes, particularly those mounted on equatorial tracking systems, depend on sidereal time to follow celestial targets with precision. Unlike solar time, forever drifting with the changing position of the sun, sidereal time remains anchored to the unchanging lattice of the stars. When astronomers at the European Southern Observatory point their instruments toward a distant star, they align their systems not to the 24-hour rhythm of human life, but to the 23-hour, 56-minute rhythm of the cosmos itself. This keeps the telescope gliding at exactly the right pace to counteract Earth's rotation relative to the stellar background, holding the target perfectly centered in view. Even space observatories such as the Hubble Space Telescope and the James Webb Space Telescope operate according to sidereal principles. Their pointing systems rely on reference stars catalogued with astonishing sub-arc second precision to maintain flawless orientation. A timing error of only 1 second translates to about 15 arc seconds on the sky, enough to soften the finest details in the images of remote galaxies. So while your day is paced by the ticking of a clock, astronomers pace theirs by the constellations. This distinction reveals that time itself is layered. One layer is built for human habits. Another orchestrates the mechanics of the universe. If you chose to live entirely by sidereal time, your day would begin 4 minutes earlier with every sunrise. After 6 months, your personal midnight would fall at noon. After 1 full year, you would return to alignment once again. And Earth's rotation is not perfectly steady either. Geological forces, ocean tides, and the shifting of mass from melting glaciers subtly alter the length of the day. The average day grows longer by about 1.7 milliseconds per century, primarily because tidal friction, the gravitational pull of the moon, gradually slows Earth's spin. Hundreds of millions of years in the past days were shorter. During the era of the dinosaurs, a day lasted roughly 22 hours. Scientists uncovered this truth in coral growth rings and layers of tidal sediments, natural timekeepers, showing that ancient Earth spun through about 400 days each year rather than the 365 of the present. Each day was shorter, but Earth's orbit around the Sun remained unchanged. This slow deceleration continues, now too subtle to notice, yet measurable with atomic clocks. To keep our timekeeping consistent with Earth's gradually slowing rotation, international time standards occasionally add a leap second to coordinated universal time. Without these corrections, the gap between solar time and atomic time would expand into minutes over the span of centuries. The International Earth Rotation and Reference System Service monitors these shifts using very long baseline interferometry and satellite laser ranging. These techniques measure Earth's rotational phase with microsecond accuracy, allowing scientists to detect even the faintest wobbles in our planet's spin. And why does this matter? Because understanding sidereal time is essential for everything from tracking satellites to steering spacecraft. When engineers send missions to Mars or farther into the deep, they must calculate launch windows based on Earth's exact rotational position relative to the destination world. A misalignment of only 4 minutes in sidereal timing could send a spacecraft thousands of kilometers off course. That is why mission control rooms so often keep both coordinated universal time and local sidereal time displayed together. Astronomical phenomena, whether occultations, eclipses, or transits, are forecast using sidereal models rather than solar ones. And if you have ever sensed that the stars appear to rise a little earlier with each passing night, that is the sidereal clock revealing itself, a quiet metronome beneath the schedule humanity has chosen to follow. It is the genuine pulse of Earth's rotation, the rhythm nature itself obeys, even as our timepieces overlook it. A familiar phrase once noted that we are a way for the cosmos to know itself. To know that cosmos, we must first appreciate the true cadence of our own spinning world, not the convenient cycle of 24 hours that we devised, but the exact rotational period inscribed in the geometry of the universe. This sidereal day, 23 hours, 56 minutes and 4 seconds, defines our planet's relationship with the wider cosmos. It governs the slow drift of the night sky, the direction a telescope must point, and the stability of celestial coordinates maintained over decades of observation. Without this reference, astronomy would lose its foundation. Yet the distinction between a solar day and a sidereal one also hints at a deeper story about how motion and time are intertwined. Those extra 4 minutes accumulate because Earth is never motionless. Our orbit adds that subtle delay with every rotation, a reminder that our world does not simply spin, it journeys around its star. Researchers sometimes describe this as compound motion, two simultaneous rotations, blending into one elegant cycle that shapes our perception of time. It is not a flaw. It is the natural imprint of a world in motion. Stand outside at midnight and look toward the southern sky. The stars that cross the meridian tonight will reach that same line 4 minutes earlier tomorrow. This steady drift explains why constellations shift, with the seasons Orion gracing winter skies and Scorpius rising in summer. The sidereal clock moves forward with quiet certainty, carrying our view of the universe onward night after night. And so when the clock strikes midnight, remember that this moment belongs only to Earth's solar timetable. The cosmos has already advanced. High above the sidereal day has completed its rotation, precise and unbroken, older than any system of human timekeeping. That is the hidden truth beneath the measure we call a day. A day is not truly 24 hours. It is 23 hours, 56 minutes and 4 seconds, plus the added motion of a planet endlessly circling its star. And that rotation, tipped ever so slightly, is the reason seasons exist, the reason storms form, the reason life flourishes. Tilted by 23.4 degrees, this small lean governs Earth's climate. If Earth were not tilted, if its axis stood perfectly upright like a flawlessly balanced spinning top, there would be no summer or winter, no shifting seasons at all. The world would remain locked in an eternal monotony, the equator forever warm, the poles forever frozen, each sunrise indistinguishable from the last. But because our planet inclines by 23.4 degrees from vertical, everything changes. This small angle, known as axial tilt or obliquity, is the reason Earth breathes in seasonal cycles. It determines when crops flourish, when oceans stir, when monsoon systems shift, and when polar ice advances or recedes. In the language of astronomy, 23.4 degrees may seem trivial, yet it is among the most consequential numbers in the history of life. The idea is simple. Earth's rotational axis is not perpendicular to the plane of its orbit around the Sunday. As the planet traces its elliptical path, the northern and southern hemispheres alternately lean toward the Sunday. When the North Pole tilts sunward, sunlight reaches the northern hemisphere more directly. The same energy is focused onto a smaller area, raising temperatures and bringing summer. 6 months later, the situation reverses. The southern hemisphere turns toward the sun, and the north fades into winter. It has long been explained that seasons are created not by Earth's changing distance from the sun, but by the tilt of its axis. At perihelion, when Earth is closest to the sun, in early January, the northern hemisphere still experiences winter because it leans away from the incoming light. Distance alters temperature only slightly. The angle of sunlight shapes the rest. This geometry defines the climate of our world. At the equator, sunlight arrives almost directly throughout the year, maintaining warm conditions. At higher latitudes, sunlight strikes at shallower angles, spreading its energy across broader areas and producing cooler temperatures. The same tilt explains why the Arctic Circle at 66.5 degrees north experiences weeks of constant daylight in summer and unbroken darkness in winter. The sun either never sets or never rises depending on the season, all dictated by simple geometry. Observations from missions like Gaia have refined our understanding of this motion. Earth's axial tilt is not fixed. It sways with a slow and deliberate grace, a motion known as axial precession, completing a full cycle over roughly 26,000 years. This gradual shift changes the alignment of the seasons, with Earth's orbit gently adjusting climate patterns across immense stretches of time. Over tens of thousands of years, the tilt itself oscillates between 22.1 degrees and 24.5 degrees, guided by the gravitational influence of the Moon and the other planets. These long rhythmic variations form what scientists refer to as the Milankovic cycles, named after the Serbian astrophysicist Milutin Milankovic, who in the year 1920 described how subtle changes in Earth's orbit and axial tilt drive the recurring advance and retreat of the ice ages. According to the Goddard Institute for Space Studies of the National Aeronautics and Space Administration, when the angle of tilt grows larger, the seasons become more intense, with hotter summers and colder winters. When the angle diminishes, the seasons soften and vast ice sheets grow. Today's tilt of 23.4 degrees sits comfortably near the middle of this range, granting Earth a remarkably stable climate that enables complex life to flourish. Without that stabilizing angle, our world would be far more hostile. Simulations reveal that a perfectly upright Earth would experience barely any seasonal contrast, leaving the poles trapped in perpetual cold and weakening global atmospheric circulation. Weather systems would flatten, the jet stream would collapse, and rainfall would lose its reliable rhythms. Agriculture, so dependent on seasonal change, would never have arisen. Even more extraordinary is the way this tilt remains steady. The Moon provides the essential stabilizing force. Its gravitational pull acts like a cosmic anchor, preventing Earth's tilt from lurching into extremes. Without the Moon's presence, computer models indicate that the tilt could wander chaotically between 0 degrees and 85 degrees, driving catastrophic climate swings every few million years. As scientists at the National Aeronautics and Space Administration have noted, the Moon may be the very reason Earth's climate has remained steady enough for life to take hold. At the poles, the consequences of tilt play out on a dramatic stage. During the Northern Hemisphere's summer solstice, around the 21st of June, the North Pole leans toward the Sun, and daylight lingers without setting for weeks. At the same moment, the South Pole is turned away, submerged in unbroken darkness. 6 months later, the situation reverses. The solstice marks the precise moment when the Sun's apparent path reaches its furthest point north or south in the sky, the outer edges of our yearly cycle of sunlight. The equinoxes around the 21st of March and the 23rd of September bring a delicate equilibrium when both hemispheres receive equal light and day and night, each span roughly 12 hours. This intricate choreography of angles shapes Earth's climate zones. It controls where deserts arise, how winds circle the globe, and where life is able to prosper. When the tilt shifts even slightly, the boundaries of ecosystems move with it. The National Oceanic and Atmospheric Administration uses this knowledge to model the planet's flow of energy. Their calculations show that during Northern Hemisphere summer, the upper atmosphere above the pole receives about 480 watts per square meter of solar power, compared to less than 100 watts in winter. This contrast energizes ocean currents, drives the circulation of air, and even sets the paths along which animals migrate. The James Webb Space Telescope now observes distant worlds with measurable axial tilts, seeking planets that might share this delicate, balancing geometry. Astronomers have identified some with extreme tilts exceeding 80 degrees, tipping their poles directly toward their stars. Such worlds endure seasons that last for years or even decades. Others rotate with barely any tilt at all, experiencing little seasonal variation. Neither extreme appears friendly to life as we understand it. Earth's 23.4 degree angle stands out as a remarkably gentle middle ground, a balance between stability and change. Carl Sagan once reflected that our world is a solitary mote suspended in the vast enveloping darkness of the cosmos. Yet this tiny lean, this slight asymmetry, is what makes the mote come alive. Even within this balance, small shifts continue. Data from the Jet Propulsion Laboratory of the National Aeronautics and Space Administration show that Earth's tilt changes by about 2.4 arc seconds, an almost imperceptible motion. But over thousands of years, it rearranges the pattern of sunlight across the latitudes. This slow adjustment of solar energy has been linked to the rhythm of glacial and interglacial epochs, the pulse of Earth's climatic past. At this very moment, Earth maintains its steady inclination, not altering its angle abruptly, but holding its orientation through each orbit. This constancy means that, as the year unfolds, our planet turns different regions toward the Sun. It is this simple geometry that allows you to stand beneath a warm summer sky at one time of year and watch snowfall at another. Climate models show that if the tilt were even slightly larger or smaller, the distribution of energy across the planet would shift enough to transform entire ecosystems. The polar ice caps would either diminish dramatically or spread deep into the continents, and even a shift of 2 degrees could redraw the global pattern of winds and storms. Every calendar ever devised, every field of crops, every migrating creature ultimately follows the quiet guidance of that tilt of 23.4 degrees. The line of sunlight that wanders north and south across the equator, known as the solar declination, is what shapes our seasons, our harvests, and the cadence of our daily existence. It is astonishing that a single value, 23.4, can wield such influence. It is the hidden architecture behind each breath of wind, every drop of rain, every leaf that changes hue and drifts to the ground. If you could step far enough away to watch our world circle the sun, you would see a turning sphere resting gently on its side, inscribing an invisible loop through the darkness. That lean, subtle yet unwavering, paints the planet with shifting tapestries of illumination and shadow throughout the year. As it has been said, we are drawn into a vast celestial choreography shaped by nature's profound forces. And when sunlight touches your face tomorrow, remember that it reaches you not because the sun has altered, but because the earth inclines at just the right angle. That inclination, that 23.4 degree tilt, may be among the most unlikely and valuable coincidences in the cosmos. Yet the tale of Earth's movement is far from complete. While the tilt crafts the seasons, time itself must continually adjust, trying to keep pace with a planet that never turns with perfect repetition. This is where the next gentle chapter unfolds into the peculiar arithmetic of leap years and the careful adjustments that hold our calendars in harmony with the drifting heavens. Part 8. Leap years are not blunders, they are corrections. Every 4 years we add a single day, and few ever pause to wonder why. It feels like a small curiosity in the calendar, a rare 29th of February that slips into the year almost unnoticed. But that added day is not an error. It is a precise adjustment, a measured correction that keeps human time bound to the true motion of Earth. The planet does not complete its orbit around the Sun in exactly 365 days. It requires 365.24219 days, which is 365 days, 5 hours 48 minutes and 45 seconds. This narrow fraction, just less than a quarter of a day, causes our calendar to creep slightly ahead of the genuine seasons each year. After 4 years, the accumulated drift approaches a full day. That is why every 4th year we insert the 29th of February, not for convenience, but out of mathematical necessity. Without this additional day, the seasons would slowly detach from the calendar. Within a few centuries, spring would arrive during what we call February, and eventually winter would fall in July. According to the Goddard Space Flight Center, leap years keep the calendar aligned with Earth's true journey around the Sunday. Without these adjustments, our system of time would steadily lose synchronization with the natural world. The concept of adding extra days is ancient. Early astronomers noticed long ago that the solar year refused to fit neatly into whole numbers. The Egyptians were among the first to formalize a 365-day calendar, but over generations they watched their New Year's Day drift away from the annual flooding of the Nile. The Romans encountered the same challenge, and in the year 46 before the Common Era, Julius Caesar mandated a reform that became the Julian calendar. The Julian system assumed the year measured 365.25 days, placing one leap day every 4 years. At first it served well, but even this system went slightly too far. The tiny excess of 0.00781 days per year, about 11 minutes, accumulated. After 128 years, the calendar had moved ahead of the true solar year by nearly one full day. By the 16th century, the misalignment had grown to almost 10 days. The spring equinox expected around the 21st of March was falling on the 11th of March. To correct the issue, Gregory XIII commissioned a new system in 1582, guided by the work of astronomer Christopher Clavius. The Gregorian calendar made one elegant adjustment. Century years, such as 1700, 1800, and 1900, would not count as leap years unless divisible by 400. This subtle rule refined the average calendar year to 365.2425 days, remarkably close to the true tropical year. The reform required an immediate shift. To restore the equinox to its proper place, 10 days were removed. In 1582, Thursday the 4th of October was followed by Friday the 15th of October. The world effectively leapt forward by 10 days to mend the flow of time. Initially, many resisted. Protestant nations rejected the papal reform for generations. Britain and its colonies did not adopt the Gregorian calendar until 1752, by which time the discrepancy had expanded to 11 days. People were bewildered and even outraged. Some believed part of their lives had been taken from them. But nothing had been stolen. Time had simply been brought back into alignment. The Earth continued its steady motion through space, while humanity gradually learned to follow its pace. Historians often describe the Gregorian reform as the most successful adjustment our species has ever made to its own measurement of time. It created a unified global framework and brought the civil calendar into alignment with the astronomical world. Today, nearly every nation on the planet relies on this system, with only a handful preserving traditional calendars for cultural or spiritual purposes. The accuracy of leap years has become more important than ever. The Jet Propulsion Laboratory of the National Aeronautics and Space Administration depends on this precise structure to chart spacecraft trajectories, plan planetary encounters, and calculate orbital pathways. A drift of only a few minutes each year would send interplanetary missions off course by thousands of kilometers. Astronomers and engineers therefore use Julian dates, a continuous count of days beginning on the 1st of January in the year 4713 before the Common Era, to avoid any discontinuity created by ordinary calendars. Yet, for everyday life, the Gregorian system remains the benchmark. Its construction ensures that the average calendar year differs from the actual tropical year by only 26 seconds. This corresponds to an error of 1 day every 3,300 years. Even so, this remarkable precision is not absolute. The Earth's rotation gradually slows because of tidal interactions with the Moon, lengthening each day by roughly 1.7 milliseconds per century. Over many thousands of years, this slight effect will demand additional refinements. Future generations of scientists may eventually need to reconsider the definitions of both a day and a year. For now, leap years maintain an extraordinary closeness to the natural rhythm of the cosmos. The International Earth Rotation and Reference Systems Service observes this delicate balance, ensuring that atomic time, defined by the oscillations of cesium atoms, remains synchronized with astronomical time. From time to time, the service adds a leap second, just as we insert leap days, so that atomic clocks remain aligned with the true rotational speed of the planet. Both seconds and days, therefore, undergo constant adjustment. The consequence is a world in which everything from daily routines to space exploration is guided by mathematical corrections quietly embedded within every calendar. Someone once said that we do not truly measure time with clocks, but with change. And that is exactly what leap years track: the shifting of Earth's orbit, the gradual slowing of its rotation, the difference between our imposed order and the motion of the universe. It is a humbling thought that even our most universal system is not fixed. It is a living structure, continually refined to match an imperfect world. Without these small interventions, history itself would slip out of alignment with the reality it describes. Consider this: every leap day is humanity's gentle recalibration of its clock to the cosmos. Every 29th of February, we quietly reconnect ourselves to the orbit that defines our year. The Earth turns, the Sun returns, and for a moment time feels perfectly measured again. This precision reaches far beyond ordinary experience. The James Webb Space Telescope operates according to strict orbital mechanics tied to solar and sidereal timing. Engineers schedule its observations months ahead using algorithms that factor in the leap year cycle. Missing one correction could shift an observation window by hours, altering the telescope's orientation with respect to its distant targets. That single extra day in February therefore matters across many disciplines, spanning everything from birthdays to the study of galaxies. It stands as a testament to humanity's desire to stay in harmony with the cosmos. When you glance at your calendar and notice that rare additional day, remember that it accounts for 5 hours, 48 minutes, and 45 seconds of accumulated drift. It reflects the difference between the time we keep and the time the Earth actually follows. It is one of the most beautiful examples of science woven quietly into the fabric of daily life. Every 4 years, we remind ourselves that precision is not a pursuit of perfection, but an act of continual adjustment. Someone once observed that science can itself be a profound source of spirituality, and the leap year embodies that sentiment. It is a union of calculation and wonder, a place where mathematics silently preserves our connection to the stars. Our timekeeping is not static. It is a collaboration between the motion of the Earth and the human mind. Each correction, each refinement, keeps us in step with the geometry of our orbit and the steady rhythm that defines a year. And within that rhythm lies another journey, the immense distance each of us travels during a lifetime, carried through space by the turning world beneath our feet. You have never been motionless, not even for an instant. Even in sleep, you are racing through the cosmos at a velocity no spacecraft has ever reached. Over the course of a century, you will drift with the Earth more than 9,000 million kilometers through space. That voyage begins the instant you are born. The hospital room in which you draw your very first breath is already hurtling through space, rotating at roughly 1,670 kilometers per hour as the planet turns beneath you. At the same time, you are circling the sun at about 108,000 kilometers per hour, drifting around the center of the galaxy at nearly 792,000 kilometers per hour, while the entire Milky Way glides toward the Great Attractor at more than 2,001,100,000 kilometers per hour. Every instant of your life is spent in motion, a seamless cascade of journeys nested within grander journeys. It has been described with remarkable clarity. Our whole solar system sweeps through the galaxy at about 220 kilometers per second, carrying everything within it along that vast trajectory. So even when you sit motionless or lie down to rest, you are traveling millions of kilometers each day. A single night's sleep, 8 hours of quiet, amounts to roughly 3 million kilometers of passage through the galactic landscape. And yet there is no hint of vibration, no gentle sway, not even the faintest murmur of acceleration. The reason is profound. The air, the oceans, the crust, the sky above all of it moves with you as a single coherent system. The stillness you feel is a kind of cosmic illusion born from shared motion. In physics, you are embedded within an inertial frame of reference, a drifting stage on which everything around you shares the same velocity. Only when that motion shifts, only when acceleration or resistance intrudes, does it become perceptible. It is the same principle that allows astronauts to float effortlessly aboard the International Space Station, not because they have escaped gravity, but because they are falling around the planet in continuous freefall, traveling 27,600 kilometers per hour along a curved trajectory that mirrors the Earth's shape. The result is a gentle, uninterrupted glide through space without any sensation of movement, and you experience a softer echo of that very same phenomenon in every moment of your existence. The Gaia spacecraft, which maps the positions and motions of more than 1.5 billion stars, has revealed that our Sun traces a subtly undulating orbit through the Milky Way, a spiraling path that rises above and dips below the galactic plane, roughly every 32 million years. As you go about the small rituals of daily life, eating, breathing, sleeping, your body is carried along that same oscillation, borne through the luminous arms of the galaxy. From a vantage point far above, one might see the solar system sweeping forward like a radiant ribbon, planets circling the sun drifting through the galaxy, and the galaxy itself drawn toward unseen structures scattered across the universe. Every human being, every drifting cloud, every grain of sand participates in this grand celestial motion. The atoms within your body, forged long ago in ancient stars, now retrace the pathways once traveled by their stellar ancestors as they journey through the galaxy. Consider the scale of this movement. In a single day, the Earth completes one rotation, carrying you 40,000 kilometers around its circumference. It proceeds another 2.6 million kilometers along its orbit around the Sun. Meanwhile, the solar system itself advances an additional 19 million kilometers through the Milky Way. Over a year, that motion swells to astonishing proportions. Across a century, your journey exceeds 7 billion kilometers. That is nearly 9 times 10 to the power of 11 kilometers, or about 9 billion kilometers of cumulative travel. And still, you feel none of it, because motion by itself is always relative. The principle of relativity tells us that no experiment conducted inside a sealed environment can reveal its uniform motion. That is why you can pour water into a glass or light a candle indoors, even as the entire planet rushes through space at extraordinary speed. In this sense, every home, every aircraft, every human body becomes a quiet chamber aboard an immense and invisible vessel, the Earth gliding silently through the cosmic ocean. Yet this journey is not perfectly smooth. The planet wobbles gently as it spins its axis, precessing like a slowly turning top. It also rises and falls slightly along its orbit due to the gravitational pull of the Moon and the planets. These delicate perturbations, measured down to tiny fractions of a second, produce minuscule shifts in the Earth's orientation, but they are significant enough for space agencies to refine spacecraft trajectories with centimeter-level precision. So while your senses cannot detect the motion that carries you through the cosmos, our instruments can trace it with breathtaking exactness. Atomic clocks carried aboard the satellites of the Global Positioning System tick at slightly different rates from those on Earth because time itself bends under the influence of motion and gravity. Without the corrections predicted by Einstein, the positions calculated by the system would wander by 10 kilometers each day. Every modern map, every aircraft following its routes across the sky, every ship tracing a path across the oceans depends upon this intricate interplay of motion and time. Our sense of being still is not merely misleading, it is a gentle misunderstanding born from living inside a moving world. Life exists within a fragile equilibrium of forces. If the planet were to halt its rotation in an instant, the atmosphere and oceans would surge onward at 1,670 kilometers per hour, racing across the continents with unimaginable violence. The serenity we experience is possible only because motion is shared, because everything participates in the same cosmic glide. Physicists call this co-moving motion. It is the same principle that explains why galaxies expand together as the fabric of space stretches around them. On the grandest scales, the universe is not a collection of fixed islands. It is a vast web of systems, moving in concert, each transporting its contents without resistance. And so, as you grow older, you are not simply traveling through time, you are being carried through the architecture of space itself. Your entire life becomes a physical trajectory plotted across coordinates that will never repeat. The location in space where you took your first step, where you drew your first breath, where you first looked up at the night sky, these points lie billions of kilometers behind you now. Every memory you hold is anchored to a different place in the galaxy. Astronomers sometimes speak of galactic coordinates to describe positions within the Milky Way. According to data from the International Space Agency, the solar system travels at roughly 7.3 kilometers per second toward a region near the constellation Hercules. By the time tonight has passed and you have slept, you will have shifted more than 630,000 kilometers in that direction without perceiving it at all. If your journey through space left a glowing ribbon behind you, it would trace a spiral around the sun, threading its way like a luminous strand woven into the fabric of the Milky Way. The James Webb Space Telescope, drifting 1.5 million kilometers from Earth, moves with us along this same celestial current. It peers into the past, gathering light that has voyaged across billions of years. Even as it drifts forward through the galaxy with the world that created it, everything we build, everything we observe, participates in this endless motion. And yet, because our senses evolved within this shared velocity, we mistake it for stillness, a comforting illusion in a universe defined by perpetual travel. One astronomer once expressed it beautifully. We are passengers aboard a tiny blue world drifting through the vast cosmic dark. That world does not simply float, it soars. Its movement dictates our nights and days, our years and seasons, even our perception of time. The next time you close your eyes to sleep, consider this. In 8 hours of rest, you will have travelled nearly the distance between Earth and the Moon without moving a muscle. And when morning arrives, you will awaken somewhere new, on a planet that has spun, orbited, and drifted millions of kilometres farther through the galaxy. So the stillness you feel is an illusion, but it is a graceful one, a quiet arrangement that protects us within the sweep of universal motion. Yet even within this beauty, our attempts to measure time have faltered, and once we lost entire days in the effort to correct it. Part 10. The 11 days that disappeared from history. Imagine opening your eyes one morning to discover that 11 days of your life had simply vanished. Not misplaced, but removed. That is precisely what happened in September of the year 1752, when people across the British Empire went to sleep on September the 2nd and awoke on September the 14th. 11 full days gone, not through conflict or calamity, but through mathematics. This peculiar moment was neither sorcery nor legend. It was the result of humanity's long struggle to define something deceptively straightforward. The duration of one genuine rotation and one genuine orbit of Earth. The story began many centuries earlier with the Julian calendar introduced by Julius Caesar in the year 46 before the Common Era. Roman astronomers, guided by Sosigenes of Alexandria, calculated that a year, the time it takes Earth to complete one orbit around the Sun, lasted 365.25 days. To account for the extra quarter day, they added one leap year every 4 years. It seemed flawless. But over the centuries, that 0.25 day estimate produced a subtle drift. The true tropical year, the interval from one equinox to the next, lasts 365.2421, 9 days, around 11 minutes, shorter than the Julian value. Those 11 minutes each year accumulated with the quiet patience of drifting sand, grain after grain, in an ancient hourglass. Over 128 years, that small discrepancy nudged the calendar a full day ahead of the seasons. After 1,500 years, the mismatch had grown to nearly 10 days. By the middle of the 1500s, the spring equinox, which should have arrived around the 21st of March, was appearing instead on the 11th of March. The motion of the sun itself had slipped out of step with the human calendar. For the astronomers of that era, this was not merely an inconvenience. It was a crisis. The equinox determined the schedule of sacred observances, the rhythm of planting, and the accuracy of navigation across the seas. The heavens no longer aligned with the dates inscribed on parchment. And so in the year 1582, Pope Gregory XIII, guided by the Jesuit astronomer Christopher Clavius, commanded a global correction. The Gregorian calendar would halt the drift by removing 10 days. Across Catholic Europe, Thursday the 4th of October 1582 was immediately succeeded by Friday the 15th of October. In an instant, the calendar was brought back into harmony with the seasons. Yet, adoption was far from universal. Protestant nations wary of papal influence held fast to the older Julian system. For almost 2 centuries, Europe inhabited 2 parallel versions of time. England and its colonies finally transitioned in 1752, by which point the Julian calendar lagged behind by 11 days. Parliament declared that the 2nd of September would be followed by the 14th of September, erasing the accumulated discrepancy at a stroke. It became one of history's most curious temporal shifts, an entire week and nearly a half swept away. A popular tale claims that furious crowds stormed the streets demanding "Give us back our 11 days." Although historians now doubt the scale of such protests, the bewilderment and suspicion of the time were very real. Contracts required revision, birthdays moved. Even George Washington found himself with 2 dates of birth, the 11th of February 1731 under the Julian reckoning and the 22nd of February 1732 under the Gregorian. Yet beneath the social turmoil lay a deeper revelation. Time as we choose to record it is not an immutable constant. It is a dialogue between the mechanics of the cosmos and the precision of human measurement. And that precision must always be refined. NASA's Goddard Space Flight Center describes the Gregorian reform as a restoration of harmony between human time and celestial time. It brought the calendar back into alignment with Earth's true orbit around the Sun, a fact later confirmed by spacecraft observations. Today, the Gregorian calendar endures as the global standard, its average year spanning 365.2425 days, a duration exceeding the tropical year by only 26 seconds. At that rate, more than 3,300 years would pass before the calendar drifted by a single day. Still, even this remarkable accuracy is not flawless. Earth's rotation is gradually slowing as lunar tides draw subtly against it. The length of a day increases by roughly 1.7 milliseconds each century. Over thousands of years, even our finest timekeeping systems will demand further refinement. That is why organizations such as the International Earth Rotation and Reference Systems Service occasionally introduce leap seconds into coordinated universal time. These tiny adjustments ensure that atomic time remains synchronized with the planet's true rotation. It is the same underlying principle that once required the 11-day correction of 1752, though now expressed in mere fractions of a second. Without these corrections, our clocks would drift away from the Sun's position. Every device, from mobile phones to orbital satellites, would slowly fall out of alignment with sunrise and sunset. It is an astonishing thought that the functioning of our entire civilization, from agriculture to navigation to the exploration of space, depends upon our capacity to measure Earth's spin with exquisite precision. Astronomy, physics, and engineering all converge on this central idea. Our planet is at once a timepiece and a vessel voyaging through space. The European Space Agency applies this reality when planning orbital transfers. Each spacecraft launch window is determined not by the human calendar, but by Earth's exact rotational and orbital relationship to the Sunday. A discrepancy of even a single second can divert a probe's path by hundreds of kilometers. In that light, the 11 days omitted in 1752 were not lost. They were the cost of restoring alignment. Humanity has adjusted its sense of time to resonate with the true rhythm of the solar system, a rhythm we can now trace with extraordinary accuracy. This precision arises from atomic clocks that rely on the measured vibration of cesium, 133 atoms, oscillating exactly 9,192,631,700 times each second. With instruments so exact, even the faint differences in gravity between a mountain summit and a valley floor become detectable as subtle shifts in the passage of time. Einstein foresaw this effect in his theory of general relativity, describing how gravity stretches and bends the flow of time itself. Experiments with atomic clocks have shown that time moves a little faster at higher altitudes, where gravity's pull is slightly weaker. In the years to come, this level of precision will reshape not only the way we measure hours and seconds, but the way we chart the surface of our world. Seen through this lens, the 11 missing days of the year, 1752, stand as a marker of progress, a reminder that our understanding of time is always advancing, always refining itself to echo more faithfully the cosmic rhythms around us. It has been said that the universe is under no obligation to make sense to us, and yet we have built tools that strive to interpret it, tools capable of aligning calendars, predicting eclipses, and guiding spacecraft across billions of kilometers with remarkable accuracy. When those 11 days were removed, it was not an alteration of history, but an act of synchronization with the true workings of the cosmos. In doing so, it became part of a lineage shaped by generations of astronomers, mathematicians, and engineers who have worked for millennia to keep human civilization in harmony with the heavens. It is humbling to realize that every date you note, every clock you check, every schedule you keep relies on this continual effort to recalibrate. From those missing 11 days to the leap seconds introduced by modern scientists, our measurement of time remains a moving target, always adjusting to follow a planet that never ceases its motion. It was once said that we are like butterflies who flutter for a single day and imagine it to be forever. Yet even within that fleeting flutter, the ground beneath us is shifting, readjusting, and correcting its rhythm against the stars. So when your eyes fall upon a calendar, when you encounter a February 29, or when you remember that 11 days once disappeared to realign human society with celestial mechanics, recognize that all of this forms part of one continuous narrative, a world in constant motion measured by minds committed to keeping pace with the vastness above. And as this reflection ends, our quiet passage through motion, time, and precision arrives at its gentle close, reminding us that every tick of every clock, from the shadow of an ancient sundial to the pulse of an atomic oscillation, is a quiet exchange between Earth and the universe. If this calm journey through time and space has offered you even a moment of stillness, I am deeply grateful you spent it here. A simple like or a soft tap to subscribe becomes more than support. It is an invitation to continue exploring the sleeping worlds of science together. And if you feel inclined, I would be delighted to know where and when you are listening. Your words, whether brief or thoughtful, shine like small stars guiding the next voyage. Until that next journey, rest easily, drift gently, and remember that even in silence we are always moving. I wish you a peaceful night, a deep and restorative sleep, and the softest dreams beneath the immense universe.